Picture the oldest light in the universe, not a metaphor, not a poet's approximation, the actual physical photons that left their source when the cosmos was 280 million years old, a sliver of time so thin against the 13.8 billion year arc of everything that it barely registers as a fraction. Those photons crossed an expanding ocean of space, stretching and cooling as they went, reddening over distances that language cannot hold, until, on the 16th of May 2025, they landed on a mirror floating silently 1.5 million kilometers from Earth. And what they carried was impossible. Not impossible in the way scientists use the word loosely as shorthand for unlikely or surprising. Impossible in the way that stops a room. Impossible in the way that means, if this is real, then something we thought we understood about the birth of the universe is wrong, not incomplete, not slightly off. Wrong. The galaxy is called MOM-Z14. It is the most distant object ever confirmed by human observation, and the team that found it, brilliant, careful, methodical scientists, published their paper with a title that, in the cautious world of academic astronomy, amounts to a shout. They called it, in the Open Journal of Astrophysics, a cosmic miracle. But MOM-Z14 is not the only thing JWST has found out there. It is not even the most disorienting thing, because at the edge of the observable universe, the James Webb Space Telescope has been finding things, one after another, that were not supposed to be there. Things that contradict not one model, not one assumption, but the entire scaffolding of ideas we have used, for decades, to explain how the cosmos grew from nothing into everything we see tonight when we look up. This is not a story about a single discovery. This is a story about what happens when the most powerful eye humanity has ever built looks back to the beginning, and the beginning does not look like what we expected. Every great instrument begins as a question. The question that built the James Webb Space Telescope was one of the oldest in human astronomy, asked in one form or another since Galileo pointed his primitive lens at the night sky and realized that the smear of the Milky Way resolved into individual stars. The question was this: how far back can we see? And underneath that question, coiled tight like a spring, was the deeper one. What was there at the beginning? For most of the 20th century, the beginning was a theoretical construct. We knew from Edwin Hubble's observations in the 1920s that the universe was expanding, that galaxies were receding from us in every direction, the farther ones moving faster than the nearer ones. Running that expansion backwards, like rewinding a film, led inevitably to a moment of extraordinary compression, a point, roughly 13.8 billion years ago, from which everything emerged. The Big Bang. The name itself is misleading, coined half-mockingly by astronomer Fred Hoyle, who didn't actually believe it. But the name stuck, the theory proved correct, and the question that followed was the one that would eventually require the greatest telescope ever built. What happened next? After the bang, after the first minutes of nucleosynthesis, forged hydrogen and helium in the proportions we still observe today, what happened in the long darkness that followed? Because there was darkness. For roughly 100 million years after the Big Bang, the universe was a cool, expanding fog of neutral hydrogen, with no stars, no galaxies, no light. Cosmologists have a name for this era that carries its own poetry. The Dark Ages. Then something happened. The first stars ignited. The first galaxies began to assemble. Ultraviolet radiation from those first stellar furnaces tore through the surrounding hydrogen gas, ionizing it, clearing it, transforming the universe from an opaque fog into the transparent cosmos we inhabit today, where light travels freely for billions of light years. This clearing period is called the epoch of reionization, and it sits at the heart of almost every question JWST was built to answer. When exactly did it happen? What drove it? What did the first galaxies look like? How quickly did they grow? For 2 decades, a collaboration of more than 1,200 scientists, engineers and contractors worked to build a machine that could answer those questions. The budget expanded from an initial estimate of roughly $500 million to a final cost of $10 billion. The delays stretched from an original launch window of 2007 to the actual launch date of December 25, 2021. 14 years of delays, a decade of cost overruns, congressional committees that came within a single vote of cancelling the program outright in 2011. The James Webb Space Telescope is, by some measures, the most complex scientific instrument ever placed in orbit. Its primary mirror consists of 18 hexagonal gold-coated beryllium segments, each 1.32 meters across, assembling into a collecting surface 5 meters in diameter, more than 2.5 times the diameter of the Hubble Space Telescope's mirror, and gathering more than 6 times as much light. The mirror is too large to fit inside any rocket fairing built. It was designed to fold origami style for launch, unfolding over 29 days in space in a choreography involving 344 individual deployment steps, each of which had to succeed perfectly. Engineers calculated that the probability of all 344 succeeding was reassuring on paper and terrifying in practice. The telescope operates not in visible light but in infrared, heat radiation at wavelengths between 0, 6 and 28 micrometers. This design choice is not arbitrary. It is the direct consequence of physics and the expansion of the universe. Light from the very first galaxies, formed when the universe was a tiny fraction of its current size, has been travelling toward us for so long that the expansion of space itself has stretched it, shifted it from ultraviolet wavelengths, through visible light, all the way to the infrared. To see the first galaxies at all, you need an infrared telescope. And to keep an infrared telescope sensitive enough to detect faint, cold, ancient light, you need to keep it extraordinarily cold, colder than 50 Kelvin, colder than most of the vacuum of space. The solution was a sunshield the size of a tennis court, 21.197 meters by 14.162 meters, made of 5 layers of a metallic-coated film called Captain. On one side of that shield, temperatures reach roughly 358 Kelvin, hot enough to boil water. On the other side, where the mirror lives, temperatures drop to 36 Kelvin, that is minus 237 degrees Celsius. The entire telescope sits in this thermal shadow, in orbit around the second Lagrange point 1.5 million kilometers from Earth, perfectly positioned where the gravitational pull of the Sun and Earth combine to keep it stationary relative to our planet, always with the shield between itself and the heat. The engineering required to achieve all of this is, in the truest sense of the word, extraordinary. Not remarkable, not impressive. Extraordinary, beyond ordinary, in the way that stands apart from anything attempted before. JWST launched on Christmas morning 2021. The Ariane 5 rocket performed so precisely that the telescope arrived at L2 with enough fuel reserves to extend its designed mission lifetime from 10 years to potentially 20 or more. Every one of the 344 deployment steps succeeded. The mirrors were aligned, the instruments powered on, and in mid-2022, NASA released the first full-color images. Images so deep, so detailed, so saturated with ancient light that scientists who had spent their careers preparing for them were still in the moment undone by them. Jane Rigby, senior JWST project scientist at NASA's Goddard Space Flight Center, "Seriously," she said, "with JWST we are literally seeing back in time to our own beginnings. That framing, seeing back in time, is not metaphor, it is physics. Light travels at 299,792 kilometers per second. When you observe an object 13 billion light years away, you are observing that object as it was 13 billion years ago. Every image JWST takes is a document from the past. The deeper you look, the older the document, and the documents JWST has been returning from the edge of the observable universe have contained, one after another, material that rewrites what we thought we knew about the opening chapters of cosmic history. To understand why the findings are so disruptive, you first have to understand what we thought we knew. You have to understand the model that has governed cosmology for decades, the model that JWST was largely designed to confirm and refine. Because that model, technically known as lambda CDM or the lambda cold dark matter model, is the foundation under everything. And what JWST has been finding with each new observation program, each new spectrum, each new record-breaking galaxy, is that the foundation has cracks in it. The cracks have been widening since the summer of 2022, and as of the moment you are watching this, no one has fully explained them away. The Lambda CDM model is the standard cosmological model. It is, among professional cosmologists, about as close to settled science as you can get without calling it settled. A framework tested against hundreds of independent observations, refined over 4 decades, capable of predicting the structure of the cosmic microwave background to extraordinary precision, capable of explaining how matter clumped into the great filaments and voids of the cosmic web we observe today. Lambda refers to the cosmological constant, Einstein's term for the dark energy that drives the accelerating expansion of the universe. CDM refers to cold dark matter, the invisible, weakly interacting mass that makes up roughly 27% of the universe's total energy content and acts as the gravitational scaffolding around which ordinary matter assembles into galaxies. In the Lambda CDM framework, galaxies build themselves from the bottom up. Small structures form first. Dark matter halos collapse, drawing in gas, which cools and forms stars. Those early stellar systems merge over billions of years, gradually assembling into larger galaxies. It is a process called hierarchical structure formation, and it was supported by every observation made before JWST with one major caveat. We had never actually seen the very first galaxies forming. We had been extrapolating from what we could see, running our models forward and backward, filling in the blanks with equations. JWST was built in part to see those first galaxies directly and check whether the extrapolation was correct. Before launch, theorists made predictions. Based on Lambda CDM and everything understood about star formation rates, the number density of early galaxies, and the rate at which matter could collapse and form stars. In the first few 100 million years, the predictions were fairly specific. At redshifts above 10, corresponding to the universe's first 500 million years, galaxies should be rare, small, dim, and low in mass. The first generation of stars, the so-called population 3 stars, were expected to be the only stellar objects for some time, their light too faint and their numbers too small to significantly ionize the surrounding hydrogen fog until roughly 1 billion years after the Big Bang. Reionization should have been a gradual, messy, extended process, finishing somewhere around 900 million to 1 billion years after the Big Bang. That timing was locked in by 2 independent lines of evidence: measurements of the cosmic microwave background by the Planck satellite, and absorption features in the spectra of distant quasars, the so-called Lyman alpha forest, that revealed the state of hydrogen gas along ancient lines of sight. JWST launched and began observing. The first high redshift galaxy candidates arrived within weeks, and the theoretical community began to feel an unfamiliar sensation, one that, in science, tends to precede either a major discovery or a major embarrassment, and the distinction can take years to resolve. There were too many galaxies. Too many of them, far too bright, far too massive, far too numerous for a universe that should, at those early epochs, have barely begun assembling its first stellar clusters. In 2022 and 2023, initial photometric observations, measurements of galaxy brightness through different colour filters which give a rough estimate of distance, suggested the presence of galaxies at redshifts above 10 that were up to 100 times more numerous than theoretical models had predicted. Some candidates appeared to be as massive as the Milky Way, despite existing only 400 to 500 million years after the Big Bang, a time frame in which, under the standard model, nothing close to that mass should have been possible. Matter simply could not have collapsed, cooled, formed stars, and built up tens of billions of solar masses of stellar material in 400 million years. The physics didn't allow it. This is what the press described rather breathlessly as JWST breaking cosmology. That framing requires some care. Science rarely breaks. It bends, it strains, it forces revisions, and the careful observation among professionals in 2022 and 2023 was that these were photometric redshifts, estimates, not confirmations. Photometry can lie. A dusty galaxy at moderate redshift can masquerade as an extremely bright one at high redshift. The real test would come from spectroscopy, the precise wavelength by wavelength decomposition of a galaxy's light that reveals its true distance through sharp, unambiguous features in the spectrum. Spectroscopy takes longer. It requires more telescope time. It requires the near-spec instrument aboard JWST, the near-infrared spectrograph, to stare at a target long enough to collect enough photons to resolve individual spectral lines. But when those spectra came back, the picture they painted was not the reassuring one that would have let everyone relax. The most extreme candidates, the ones that seemed too massive, too bright, too far back, were revised downward as expected. Some of the most alarming photometric estimates were indeed false alarms. But many of the high redshift candidates were confirmed, and what the confirmed detections revealed about the early universe was not a return to normality. It was the opening of a deeper set of questions. This is what I find genuinely unsettling about the JWST data, not the individual records, not the specific galaxies, but the pattern. JWST was not supposed to find 100 times more bright galaxies than expected at the universe's earliest epochs. Even after the extreme outliers were revised down, the galaxy luminosity function, the number of galaxies at each brightness level at high redshift, was consistently above what the models predicted, not by 10%, not by a factor of 2, by an order of magnitude or more in some redshift bins. And in the JWST survey, the JWST Advanced Deep Extragalactic Survey, which used approximately 770 hours of telescope time from the JWST Cycle 1 guaranteed programs, a patch of sky over the DX South Field, smaller than a postage stamp held at arm's length, revealed more than 45,000 galaxies. Thousands of those galaxies existed in the first billion years of cosmic time, not dozens, not hundreds, thousands in a sliver of sky, in an era when the universe should have been populated by only the most primitive stellar systems. This is the first abundance crisis. Not my name for it. The shape of the problem is recognized throughout the field, though different papers frame it differently. The universe at 10, at look-back times beyond 13 billion years, appears to have been manufacturing bright, massive, chemically enriched galaxies at a rate that the standard model of structure formation cannot comfortably account for. And there are three possible explanations. The star formation rate in the early universe was dramatically higher than our models suggest. Or galaxies in the early universe were far more efficient at converting gas into stars than any galaxy we observe today. Or, and this is the option that keeps theorists up at night, the lambda CDM model itself needs modification at the highest redshifts. Perhaps dark matter does not behave exactly as assumed. Perhaps the initial conditions of the universe, after the Big Bang, allowed for structures to grow faster than the standard model permits. Perhaps there is new physics. None of those options is comfortable. All of them are open, and while the community debated them, JWST kept observing. And with each new observation cycle, the picture grew more detailed, more puzzling, and more thrilling, because the galaxy abundance problem was only the beginning. The problem of something that should not exist, three problems, running simultaneously, each one connected to the others through threads so tangled that pulling on any one of them risks unraveling the whole tapestry. This is where the JWST story becomes genuinely complex, where the data stops being a collection of astonishing images and becomes something more uncomfortable, a systematic challenge to the framework that underlies modern cosmology. The first thread is reionization. The second is a population of objects called little red dots. The third is the supermassive black hole problem, and they are linked in ways that may be the most important insight in extragalactic astronomy since the discovery of dark energy. Begin with reionization. We established in the last chapter that the standard model, anchored by Planck CMB measurements and Lyman alpha forest data, places the end of reionization at roughly 1 billion years after the Big Bang. This timing was one of the most secure results in modern cosmology, confirmed by multiple independent methods, consistent with galaxy formation models, considered reliable enough to be used as a calibration point for simulations. Then JWST began observing the epoch of reionization directly, identifying individual galaxies responsible for ionizing the surrounding hydrogen, mapping the ionized bubbles they carved in the primordial fog, counting the extreme ultraviolet radiation pouring from thousands of early galaxies simultaneously. The accounting, as Julian Munoz of the University of Texas at Austin phrased it, was suddenly off. The galaxies JWST found in the first billion years were not just numerous, they were extraordinarily efficient producers of ionizing radiation. If you take the JWST census of early galaxies at face value, if you trust the photon counts and the luminosity functions and the escape fractions of ionizing radiation that JWST spectroscopy implies, then you are forced to an uncomfortable conclusion. Those galaxies could have ionized the universe's hydrogen fog not by 1 billion years after the Big Bang, but by somewhere between 550 and 650 million years after the Big Bang, some 350 million years earlier than current models demand. And here is why that matters more than it might initially seem. The cosmic microwave background, the afterglow of the Big Bang, the oldest light we can observe with any instrument, constrains reionization's timing independently. The CMB measurements made by the Planck satellite are extraordinarily precise. They tell us how much hydrogen was neutral at the time the CMB photons were released, and by extension they constrain how long the epoch of reionization lasted and when it ended. If JWST's implied timeline is correct, if reionization really ended 350 million years early, then the Planck CMB data should look different. The Lyman alpha forest should look different. There would be observable consequences in data we have already collected, and they are not there. Munoz and his colleagues published this tension in the monthly notices of the Royal Astronomical Society in October 2024. They were careful about language. They called it a tension, not a contradiction, the appropriate scientific term for a discrepancy between datasets that does not yet rise to the level of a definitive conflict, but they were also direct about its significance. The discrepancy requires either new physics in the early universe, perhaps more recombination events than current models assume, where ionized protons and electrons recombine back into neutral hydrogen and slow the overall reionization process, or systematic errors in the JWST photometry or spectroscopy. And systematic errors, while always possible, have been methodically hunted and largely eliminated by teams that have spent 3 years verifying their calibrations. This is the reionization tension, and it is the clearest sign yet that the Standard Model's timeline of cosmic history may need to be revised. Now the second thread, the little red dots. This is the phenomenon that most surprised me when I spent time working through the literature, and I find the combination of their strangeness and their abundance genuinely haunting. Little red dots, abbreviated in the literature as LRDs, are a population of compact, extremely red point source objects that appeared in JWST's deep fields almost immediately after the telescope began science operations. As of 2025, 341 confirmed LRDs have been identified. They were completely unknown before JWST. Every telescope that preceded it, including the Hubble Space Telescope with its 30-year archive of deep fields, had either missed them entirely or confused them with something else. They are small, smaller in angular extent than almost any other object at similar distances. They are red, far redder than a simple dusty galaxy would explain, and they are abundant in a way that is statistically impossible to dismiss as a selection effect. They appear throughout the deep fields, clustered preferentially in the first 1 to 2 billion years of cosmic time, and their light has a spectral shape that doesn't match any class of objects previously catalogued with confidence. 3 competing explanations have been proposed, and none of them is unambiguously correct. The first explanation is that LRDs are extremely young, extremely compact galaxies, undergoing a burst of star formation so intense that billions of solar masses of stars are being born in a region barely a few hundred light years across, smaller than some of the star-forming regions in our own Milky Way. The red colour would then arise from dust absorption and from the light of the hot young stars themselves. The second explanation is that LRDs are young supermassive black holes. active galactic nuclei in the earliest stages of growth, surrounded by dense clouds of neutral gas that explain their redness, their compactness, and their unusual spectra. This is the explanation favoured by a landmark paper published in Nature in 2025, which modelled LRDs as supermassive black holes embedded in dense ionised gas halos. These black holes, under this model, are overmassive relative to their host galaxies, a property that should not exist under the standard picture, in which a black hole grows alongside its host galaxy in a coevolutionary dance regulated by feedback. If LRDs are overmassive black holes, they broke that coevolutionary rule in the universe's first billion years, and we do not know why. The third explanation, proposed by researchers at Penn State, is perhaps the most extraordinary, that LRDs could be the observed signatures of so-called black hole stars, hypothetical stellar objects composed almost entirely of infalling gas surrounding an intermediate mass black hole, objects that have never been directly observed before, objects that exist at the theoretical boundary between a star and a black hole. This explanation is speculative, but the fact that it is being seriously considered in peer-reviewed literature tells you something about the degree to which conventional explanations have struggled. What all three explanations agree on is that LRDs are unexpected. They were not predicted, not in lambda CDM simulations, not in galaxy formation models, not in any theoretical framework for the early universe that was developed before JWST. 341 of them have now been confirmed, and each one is a puzzle in itself, and together they represent a population of objects whose nature, origin, and implications for cosmology remain. In the word that appears over and over in the literature, mysterious, the confirmed supermassive black hole in Caneus LRDZ86, announced by ESA in November 2025, is perhaps the most clarifying data point yet. In a galaxy just 570 million years after the Big Bang, a galaxy so young it has barely begun producing heavy elements, a galaxy so compact that its entire stellar mass would fit within a region far smaller than the Milky Way, sits a supermassive black hole that is not merely present, but actively growing, consuming matter at a rate described by the Discovery team as far faster than we would expect in such a galaxy at this early time. And it is overmassive. The ratio between the black hole's mass and the stellar mass of the galaxy around it is not close to the ratio observed in the local universe. The black hole is, relative to its host, much larger than it should be. Co-evolutionary relationship between black holes and galaxies. The relationship that decades of observation have shown to be remarkably consistent was already being violated when the universe was less than 600 million years old. This is the black hole formation paradox. Supermassive black holes containing millions or billions of solar masses do not grow quickly, even assuming constant maximum rate accretion, a theoretical ceiling called the Eddington limit. Growing a black hole from a stellar mass seed to the masses observed in the earliest LRDs requires timescales approaching or exceeding the age of the universe at that epoch. There simply was not enough time, under standard black hole growth models, for these objects to be where they are. Either they began as something much more massive than a typical stellar black hole, perhaps through the direct collapse of massive gas clouds bypassing the usual stellar life cycle, or they grew faster than physics currently allows, or the black holes we are seeing are not what we think they are. And now the third thread, which runs beneath both of the others and connects them. The reionization crisis and the black hole formation paradox are not independent problems. They are likely symptoms of the same underlying cause. Early universe was producing more ionizing radiation than expected because it contained more bright, massive objects than expected. Those bright, massive objects include both the overly numerous luminous galaxies and the LRDs. And if the LRDs are, as the 2025 Nature paper suggests, growing supermassive black holes, then those black holes themselves would contribute ionizing radiation in quantities that the reionization models did not account for. The thread connects more objects, more mass, more ionizing photons, faster reionization, discrepancy with Planck, discrepancy with Lyman alpha. a chain of consequence stretching from the nature of the first compact objects all the way to the timing of one of the most fundamental phase transitions in cosmic history. This is the architecture of the problem. Three tensions, one underlying source. And at its heart, the question of how the universe's first structures formed so quickly, grew so massive, and ionized the cosmos so efficiently, in a time frame the Standard Model says should have been physically impossible. But while this problem was being assembled in the literature, JWST was doing something else simultaneously. It was extending the record for the most distant object ever observed, again and again, each new record carrying in its light new information about a universe even younger than the one before. And in the most recent record, a galaxy called MOV Z14 confirmed in May of 2025, the anomalies did not go away. They arrived wrapped in one of the most direct and specific pieces of unexpected chemistry ever returned from the edge of the observable universe. On May 16, 2025, the James Webb Space Telescope, using its NIR-spec instrument in a configuration called the prism mode, collected enough photons from a smudge of light in a deep field image to resolve its spectrum. The team, led by Rohan Naidu of MIT's Kavli Institute for Astrophysics and Space Research, stared at the resulting data. The spectrum showed a sharp Lyman alpha break, the characteristic signature that occurs when light from a distant galaxy is absorbed by neutral hydrogen along the line of sight, creating an abrupt cutoff at a specific wavelength that can be used to calculate the galaxy's redshift. The break was clear, the redshift was unambiguous. It was Z14.44, a redshift of 14. 44 means that the light reaching JWST's mirror has been travelling for approximately 13.5 billion years. The universe at the moment this light was emitted was 280 million years old. That is 280 million years, not 280 million years ago. 280 million years into the total 13.8 billion year story. The fraction is almost too small to state without feeling the inadequacy of the numbers. The light JWST collected from Z14 was emitted when the universe was roughly 2% of its current age. The previous record holder, a galaxy called JWST Z14-0, confirmed by the same JWST survey team in a paper published in May 2024, had held the record at Z1432, corresponding to 290 million years after the Big Bang. Z14's light is from 10 million years earlier. In terms of cosmic time, that's a narrow margin. In terms of what it means for our picture of the early universe, the difference is significant, not because of those 10 million years, but because of what Z14 reveals about itself. Z14 is not a faint, dim smudge, barely scraped from the noise. It is bright, remarkably, disquietingly bright for an object at that distance and that age. Naidu and his team chose the word miracle for their paper title not hyperbolically, but because the brightness of Z14 sits at the extreme tail of any reasonable distribution for what a galaxy at that redshift should look like. To produce the observed flux, Z14 must contain, at a minimum, an extraordinary population of massive young stars. Stars producing light in quantities that, per unit mass, far exceed what nearby galaxies produce today. And then there is the nitrogen. In the spectrum of Z14, the team detected nitrogen emission lines, specifically the N3 and NIV lines, spectral features associated with ionized nitrogen that require not just the presence of nitrogen, but the presence of radiation energetic enough to ionize it, and a gas environment dense and hot enough to produce the emission. And the nitrogen itself is the problem. Nitrogen is not a primordial element. Hydrogen and helium emerged from the Big Bang directly in the proportions we observe. Carbon, oxygen, and the heavier elements were forged later, in the interiors of stars and in the explosive deaths of those stars as supernovae. Nitrogen, specifically, is produced in abundance primarily by massive stars, stars with masses above roughly 25 solar masses, through what is called the CNO cycle. And those massive stars need time to form, to live their lives, to enrich the gas around them with their expelled atmospheres, before the next generation of stars forms in that enriched gas. At 280 million years after the Big Bang, there has not been time for this cycle to play out in the ordinary way. Not for the amounts of nitrogen MOM Z14's spectrum implies. The conventional stellar production pathway, big star forms, lives for a few million years, dies and enriches its surroundings. Next generation forms in enriched gas, requires sequential generations of stars over hundreds of millions of years. MOM Z14 has had at most 2 or 3 generations of stars, probably fewer. The explanation the MIT team finds most compelling is also the most extraordinary. MOM Z14 may host supermassive stars, individual stellar objects hundreds of times more massive than the Sun, far beyond anything observed in the local universe, burning so hot and living such brief, furious lives that they would be nearly impossible to detect directly. Supermassive stars, in models developed over the last decade, are predicted to be extraordinarily efficient producers of nitrogen precisely because of their extreme internal temperatures and the CNO cycle operating at an accelerated rate in their cores. If MOM Z14's nitrogen abundance comes from supermassive stars, then the galaxy is not just a distance record. It is the first direct chemical evidence that the first generation of stellar objects in the universe included stars of a size and nature we have never directly observed. Stars whose descendants may be the population 3 stars that theorists have predicted for half a century, but which have never been definitively confirmed. Rohan Naidu and his team noted something else remarkable. The ancient stars in the outer halo of our own Milky Way, the oldest surviving stellar populations, formed in the universe's first billion years and preserved as fossils of that era, also show anomalously high nitrogen abundances. This is a feature that has puzzled stellar archaeologists for years. The fact that MOM Z14, 280 million years into cosmic time, shows the same chemical signature as the most ancient stars in our own galaxy, creates a connection across 13 billion years of cosmic history. The nitrogen in MOM Z14 may be the same kind of nitrogen, from the same kind of supermassive progenitor stars, that ended up, billions of years later, in the ancient stars orbiting the outer reaches of our galaxy. We are, in the most literal available sense, looking at our own origin chemistry from across the observable universe. MOM Z14 also shows evidence of clearing. Ionized gas in its immediate environment, a bubble of transparent hydrogen carved by the galaxy's own radiation. This is significant because at Z1444, the universe should still be heavily neutral. The epoch of reionization was ongoing. The universe's hydrogen fog was not yet fully cleared, but MOM Z14 has blown its own local bubble, clearing the space immediately surrounding it. This is exactly the process that, replicated across thousands of early galaxies simultaneously, would eventually complete reionization. MOM Z14 is not a passive observer of reionization. It is an active participant, one of the first agents of the largest phase transition in cosmic history, and yet the luminosity function problem remains. MOM Z14 is one of a population of bright, compact galaxies at Zeta 10 that is roughly 100 times more abundant than pre-JWST models predicted. Jacob Shen, a postdoctoral researcher on the MIT team, was direct. There is a growing chasm between theory and observation related to the early universe. A growing chasm, not a slight discrepancy, not a modest tension, a chasm. The two most tractable explanations currently in the literature are these. Either early galaxies were far more efficient at converting gas into stars than any galaxy observed in the local universe, perhaps through lower metallicity gas that collapses more readily, or through a higher gas fraction in early dark matter halos, or there is a population of active galactic nuclei contributing to the bright galaxy count, meaning the galaxies being counted are not purely stellar, but include the light of feeding supermassive black holes. The LRDs re-enter the picture here. If LRDs are predominantly AGN, active galactic nuclei feeding black holes, then their brightness is not the brightness of stars, and their inclusion in galaxy luminosity functions distorts the count. Removing them would bring the observed numbers closer to predicted numbers, but removing them does not explain what they are, where their black holes came from, or why those black holes are so overmassive. The revelation from MOMM Z14 is, in the end, not a single answer. It is a higher resolution version of the same question. Something profound and as yet unexplained happened in the universe's first few 100 million years. Structures formed too quickly, grew too massive, produced too much light, carried chemical signatures of stellar populations far more extreme than any we observe today, and 280 million years into the universe's history, closer to the Big Bang than any object we have ever directly observed, we can see it happening. The question of what it means for everything that came after, for the Milky Way, for the solar system, for the chemistry of life on Earth, is not a question JWST can yet answer, but it is a question that, before JWST, we could not even properly formulate. In 1989, at a meeting held at the Space Telescope Science Institute in Baltimore, a young astronomer named Garth Illingworth chaired a committee tasked with one of the most audacious intellectual challenges in the history of modern science: defining what the next great space telescope should be. The Hubble Space Telescope had not yet launched. It would reach orbit the following year, but the astronomical community, with the peculiar forward-looking ambition that characterises the field, was already asking what would come after it. Illingworth's committee needed to look past a telescope that didn't exist yet and imagine the one that would succeed it, decades into a future no one could fully see. Illingworth was then at the University of California, Santa Cruz, where he would spend most of his career. He was not yet the astronomer he would become, the one whose name would appear on JWST proposal documents, whose decades of advocacy and scientific judgment would help shape the observatory's core science goals. He was a researcher in extragalactic astronomy, specializing in the evolution of galaxies, working with the instruments of the time, instruments that, compared to what he was imagining, were children's toys. The committee he chaired that year concluded that the primary scientific goal of the next great space telescope should be to detect the first light in the universe, to see the first galaxies, to observe the transition from darkness to illumination that marked the dawn of the cosmos. That recommendation, embedded in a report that would be updated and revised over the following decade, became the seed from which JWST grew. Illingworth spent the next 3 decades helping to nurture it, serving on proposal teams, contributing to science case documents, advocating in front of committees, watching budgets explode and schedules slip and political opposition mount, and continuing year after year to argue that the science was worth it. He was not naive. He understood the risks. He knew that telescopes of this ambition had a history of cost overruns and delays, that the community had already weathered the embarrassment of Hubble's flawed mirror in 1990, and the decade of work required to correct it. He knew that a telescope costing $10 billion would face scrutiny no previous observatory had faced. And he knew, with the peculiar clarity that comes from spending decades thinking deeply about a problem, that the science JWST could do was unlike anything that had ever been done before. Not incrementally better, categorically different. When JWST launched on Christmas Day 2021, Illingworth was not young. He had been working toward this moment for 32 years. He watched the Ariane 5 rocket rise from the Guiana Space Center in Kourou, French Guiana, and felt something that, in an interview with the Santa Cruz Sentinel, he described with characteristic understatement. He said, "I said stupid things like wow, that word wow, sitting inside quotation marks in a newspaper interview, attributed by a careful, precise scientist to himself with a kind of self-deprecating amusement, is one of the most human moments in the entire JWST story." Here was a man who had spent 3 decades writing equations and submitting proposals and sitting in committee rooms, arguing about detector sensitivity, Marika boating and launch windows. And when the moment came, when the rocket lifted and the gamble became real, the language of science left him and all that remained was a single syllable. Illingworth co-leads the JDES survey, the JWST Advanced Deep Extragalactic Survey, which is, by some measures, the most scientifically productive observation program in the telescope's first 3 years. JWST uses approximately 770 hours of Cycle 1 guaranteed time, primarily from the NIR-CAM and NIR-SPEC instrument teams, to observe two of the most iconic deep fields in astronomical history. The DJWST South and DJWST North fields, the same regions of sky that Hubble's deep field images had made famous in the 1990s. Illingworth had been one of the scientists involved in the Hubble Deep Field program too. He had watched those images transform our understanding of the universe's population of galaxies. Now with JWST, he was watching it happen again, but at redshifts, at depths, at detail levels that Hubble could never approach. First JWST images returned more than 45,000 galaxies from the South Field alone, in a patch of sky measuring roughly 10 square arc minutes. To hold that number for a moment, 45,000 galaxies, each one a system containing hundreds of millions to hundreds of billions of stars, each one a world of worlds, most of them far older and farther away than anything Hubble had resolved clearly, and embedded in those 45,000, hundreds of galaxies from the universe's first billion years. Galaxies that had never been seen before, that had never been suspected in such numbers, that directly contradicted the models Illingworth had helped develop over the same decades he had spent campaigning for JWST. I find something genuinely moving about that symmetry. A scientist spends 3 decades building an instrument to test the models he and his colleagues have developed. The instrument works better than anyone hoped, works beyond its requirements in sensitivity and stability, and what it finds is that the models are wrong. Not wrong in a small way. Wrong in a way that means the early universe was fundamentally different from what those models predicted. The thing Illingworth built rewrote the understanding that Illingworth helped construct. There is a word for that. It is called science doing its job. In a later interview, this time with the Lookout Santa Cruz, Illingworth described the experience of seeing the early JAD's data. He said the discoveries were both challenging and exciting. A pairing of adjectives that, from a man of his temperament and precision, says a great deal. Challenging means, we don't understand this yet. Exciting means, that's why we built the telescope. The two feelings exist simultaneously, and the people doing this work live in both of them at once. But the human cost of JWST, the personal dimension of the 30-year marathon, is not only Illingworth's story. It belongs to the 200 people who worked on the telescope's construction and deployment, the engineers who designed the folding mirror system and spent sleepless nights during deployment, wondering if each of the 344 steps would succeed. It belongs to the scientists who submitted observation proposals that were not selected, whose careers took different directions because the years of delay meant that other priorities shifted. It belongs to the graduate students who began their PhDs in astronomy in the 2010s, knowing that JWST was coming, calibrating their research plans around an instrument that had been about to launch for a decade before it actually did. And it belongs, in a particular way, to Jane Rigby, the senior JWST project scientist who oversaw the commissioning period, who guided the telescope from its first light images through the calibration procedures that would determine its ultimate scientific capability. Rigby has spoken publicly about the personal intensity of those first months, the knowledge that every calibration decision would shape a decade or more of science, the weight of having 200 people's life work and $10 billion of scientific investment resting on the quality of the choices being made day to day. She described it with characteristic directness. With JWST, we are literally seeing back in time to our own beginnings. The hour in that sentence carries both the scientific and the personal, our galaxy's beginnings, our species' beginnings, our understanding of where we come from. There is one further piece of the human story that deserves its place here. In 2024, at the International Space Science Institute in Bern, Switzerland, a 2-week breakthrough workshop brought together more than 50 leading cosmologists and galaxy formation experts from across the world, co-chaired by Angela Adamo, Pascal Oesch, and Antonella Nota. The stated goal was to synthesize the first 3 years of JDJ data on the early universe and produce a consensus view of what had been learned. The result was a landmark paper published in Nature Astronomy in 2025, running to dozens of pages and representing the collective judgment of the field's leading minds. Its title was The First Billion Years According to JWST. Antonella Nota, the ISSI Executive Director, described the workshop with words that capture something essential about the human enterprise of science. This is a living moment in science. The findings are extraordinary, but so is the way the community is coming together here, across specialisms, across borders, to make sense of them. Across specialisms, across borders. Hundreds of people from dozens of countries, speaking dozens of first languages, united by the shared project of understanding a universe that does not care about any of those distinctions. The most distant galaxy ever observed, MOMZ-14, was found by a team at MIT, confirmed with instruments built by European aerospace agencies, operated by a space telescope funded by American, European and Canadian governments, described in a paper reviewed by scientists from universities on 4 continents. This is what the most ambitious human projects look like when they succeed. Not a single hero, a civilization paying attention. Garth Illingworth is now retired from his position at UC Santa Cruz. He continues to work on the science. He continues to co-author papers. The telescope he spent 3 decades helping to build is still, as of mid-2026, operating nominally with fuel reserves, suggesting it could remain operational into the 2040s. Every new observation program it executes builds on the foundation he helped lay in a committee room in Baltimore in 1989 when he was asked to imagine the future of astronomy, and chose to imagine not something incremental, but something that would change everything. He was right. It has changed everything, including, quietly and profoundly, everything he thought he knew. Let me tell you what is at stake. Not as an exercise in drama, not to inflate the significance of what is, in the everyday sense, a collection of photons recorded by a sensitive detector, but because the implications of what JWST is finding at the edge of the observable universe cascade, one into another, in a chain of consequence that reaches from the physics of the first stars all the way to the question of whether life like ours is a predictable feature of cosmic history or a vanishingly rare accident, start with the immediate scientific stakes. The lambda CDM model, the standard model of cosmology, is the most precisely tested physical theory of the 20th century's second half. It has survived confrontations with data that would have destroyed lesser frameworks. It correctly predicted the pattern of temperature fluctuations in the cosmic microwave background at a precision of 1 part in 100,000. It correctly predicted the ratio of hydrogen to helium produced in the first 3 minutes after the Big Bang. It correctly predicted the large-scale structure of the universe, the cosmic web of filaments and voids that galaxy surveys have mapped over the last 3 decades. These are not small achievements. They are the reason that when JWST found things that didn't fit, the first response of the community was not to abandon lambda CDM, but to look for the mistake in the data. But the data have been checked and rechecked, and the tensions have not resolved. They have deepened, and in some cases worsened, with each new observation cycle. The most precisely measured version of the tension is not in galaxy counts or reionization timing. It is in the Hubble constant, the rate at which the universe is currently expanding. This is the Hubble tension, and it predates JWST, but JWST has made it worse. The Hubble constant, measured using the CMB and the lambda CDM model, gives a value of approximately 67.4 kilometers per second per megaparsec. The Hubble constant, measured using local distance indicators, Cepheid variable stars, type Ia supernovae, gives a value of approximately 73 kilometers per second per megaparsec. These two values disagree by roughly 9%, and the statistical significance of that disagreement is now above 5 sigma, the threshold conventionally used in physics to declare a discovery. The two measurements cannot both be right if the lambda CDM model is correct, because the model predicts a single, consistent expansion history. Something is wrong, and the community cannot agree on whether it is a systematic error in one of the measurements or genuine new physics. JWST has now measured the Hubble constant through several independent methods. None of the measurements has resolved the tension. Some have made it worse. And in 2025, an additional measurement of the Coma Galaxy cluster revealed it to be 38 million light-years closer than lambda CDM predicts, a discrepancy that extends the Hubble tension from the distant universe into what astronomers call our cosmic backyard. If the Hubble tension is real, if it is not a systematic error, then it implies that either the nature of dark energy is more complex than a simple cosmological constant, or the nature of dark matter is not quite what the CDM framework assumes, or there is new physics in the very early universe that altered the expansion history before the CMB was emitted. All three options are, in the language of physics, exotic. All three require significant modifications to the most successful cosmological model ever built. Now raise the stakes one level. The Hubble tension and the early galaxy abundance problem and the reionization tension are not independent. They are all symptoms of a potential failure mode in lambda CDM. And lambda CDM is not just a theory about the universe's expansion. It is the framework that predicts the formation of galaxies, the distribution of dark matter halos, the rate at which structures grow, and ultimately the environments in which stars and planets form. If the model needs modification, if the early universe evolved faster, more efficiently, through mechanisms currently unknown, then our understanding of how galaxy formation proceeds is incomplete. And galaxy formation, in the end, is the story of how the raw materials of chemistry and complexity were assembled into systems capable of hosting stars with planets and planets with chemistry. Consider the population 3 stars, the universe's first stars, formed from pristine hydrogen and helium with no heavier elements, predicted by theory but never, until possibly now, directly observed. Population 3 stars are cosmologically significant, not because they were the first light in the universe, though that alone would make them remarkable. They are significant because they were the first forges, the first stars to produce carbon, oxygen, nitrogen, iron, and the 100-odd elements heavier than helium in their interiors, and to expel them into space in their deaths. Without population 3 stars, there is no interstellar medium enriched in heavy elements. Without enriched medium, there is no second generation of stars capable of hosting rocky planets. Without rocky planets, there is no surface chemistry, no liquid water, no biology. The suspected detection of population 3 stars in the galaxy LAP-1b, reported in late 2025, is therefore not merely a milestone in observational astronomy. It is a potential window into the origin of the chemical conditions that made complex chemistry, and eventually life, possible anywhere in the universe. The analysis, led by Ari Visbal of the University of Toledo and colleagues, identified LAP-1b as a strong population 3 candidate, a system at redshift z 6.6, gravitationally lensed to amplification by a foreground cluster, showing spectral features consistent with the light of very massive, extremely metal-poor stars. The system formed in a dark matter halo of approximately 50 million solar masses, exactly the environment theoretical models predicted as the cradle of first stars. If confirmed, LAP-1b is the first direct observational evidence that population 3 stars existed. Not an implication, not an inference. A detection. The population 3 stars and the chemical enrichment they produced set the stage for everything that came after them. Every generation of stars that has formed since the universe's first billion years has formed from gas partly enriched by population 3 predecessors. The iron in your blood, the calcium in your bones, the oxygen in your lungs. These elements trace a lineage back through billions of years of stellar generation to the original forges of the cosmic dawn. Seeing those forges directly for the first time, in a gravitationally lensed smear of ancient light detected by an infrared telescope floating at the Earth-Sun Lagrange point, is the kind of moment that deserves more than the word discovery. it deserves the recognition that we have, in the most literal available sense, glimpsed our own origin. But the stakes do not stop at chemistry. They extend to the question of dark matter itself. Because if lambda CDM needs modification at the highest redshifts, if structure formed faster and more efficiently than the cold dark matter paradigm predicts, then one of two things must be true. Either the baryonic physics, the gas cooling rates, the stellar feedback, the supernova efficiencies, are more extreme in the early universe than currently modelled, or dark matter in the early universe behaved differently than the cold, collisionless, non-interacting particles that lambda CDM assumes. And if dark matter behaved differently, if it was warmer, or if it had self-interactions, or if it decayed or annihilated at rates the standard picture doesn't allow, then the entire particle physics program aimed at detecting dark matter in underground laboratories, which has so far found nothing, may be searching for the wrong thing. This is the civilization-level implication. The James Webb Space Telescope, launched to observe the first galaxies, may have generated the first clear empirical signal that the universe's two dominant components, dark matter and dark energy, are not what our best theories say they are. And if that is true, then the standard model of particle physics, like lambda CDM in cosmology, has a regime in which it fails. And finding that regime, characterizing its failure modes, understanding what replaces it, is the work of the next century of physics. There is one more escalation that I want to be precise about, because it is often misstated. JWST has not disproven the Big Bang. It has not found evidence against the universe's age. The 13.8 billion-year timeline, anchored by multiple independent methods, is not under serious observational pressure. What is under pressure is our understanding of how the universe evolved in its first few 100 million years. What physical processes dominated, how fast structure formed, what the first stars and galaxies were like. The Big Bang framework itself, the hot, dense early state and the subsequent expansion, is as firmly supported as ever. The questions are entirely in the details, in the galaxy abundance function, in the timing of reionization, in the mass spectrum of the first black holes, in the chemical composition of the earliest stellar populations. But the details matter. In science, as in most things, the devil lives in the details. And the details that JWST is returning from the edge of the observable universe are, one by one, forcing cosmologists to confront the possibility that the story of cosmic history, the story they have been telling for 40 years, refining and calibrating and testing against every available dataset, may have a chapter they got wrong, which raises a question that has been wrestling with professional cosmologists since mid-2022 and for which a fully satisfying answer has not yet emerged. What would it actually look like to get that chapter right? Let me be honest about something at this point. Because the temptation in a story like this is to let the drama run ahead of the evidence, to let the extraordinary nature of what JWST has found slide into an overclaim about what it means. The data are extraordinary, the tensions are real, but the resolution of those tensions is not yet written, and in the gap between the data are surprising, and the model is definitively wrong, lies an enormous amount of careful scientific work that deserves its full complexity. Begin with the galaxy abundance problem. The early claim that JWST found galaxies up to 100 times more numerous than predicted at Zeta 10 has been refined considerably by 3 years of follow-up work. Several of the most extreme cases from 2022, when the telescope had just begun operating and calibrations were still being validated, were indeed photometric artifacts. Objects that appeared to be at redshift 12 or 13 were, on spectroscopic follow-up, found to be at redshift 4 or 5, still distant but not at the cosmological frontier. Dust, as it often does, was part of the story. Heavily dust-obscured galaxies at moderate redshift can mimic the photometric dropout signature of extremely high redshift sources. But, and this is the critical but that prevents a comfortable resolution, the spectroscopic confirmation of genuine high redshift galaxies has also been extensive. JDAS alone has spectroscopically confirmed dozens of galaxies at 10. The galaxy JWST G14-0, confirmed at Z1432 in May 2024, was not a photometric artifact. MOM G14, confirmed at Z1444 in May 2025, was not a photometric artifact. And the luminosity function, the number of confirmed galaxies at each brightness level at high redshift, remains, even after the revision of the extreme outliers, above the pre-JWST theoretical predictions by a factor that ranges from a few to roughly an order of magnitude, depending on the redshift bin and the theoretical model being compared against. What theoretical explanations have been proposed, and how well do they hold up? The first and most conservative explanation is that the efficiency of converting gas nests into stars in the early universe was higher than standard models assume, because the gas was metal poor. This is a physically plausible mechanism. Low metallicity gas, lacking the heavy elements that act as coolants in present-day molecular clouds, behaves differently. It can fragment differently, form stars at different mass functions, and potentially convert a higher fraction of its total mass into stars per unit time. Simulations by several groups have explored this parameter space and found that modest increases in star formation efficiency, within plausible physical limits, can account for a factor of a few increase in the bright galaxy luminosity function without requiring new fundamental physics. The problem with this explanation, satisfying as it would be, is that it doesn't stretch to cover the full observed excess. A factor of a few falls short when the data show factors of many at the highest redshifts and brightest luminosities. The explanation covers part of the ground, but not all of it. The second explanation is AGN contamination, the suggestion that a significant fraction of the galaxies contributing to the high redshift luminosity function are not, in fact, star-forming galaxies at all, but are instead active galactic nuclei, feeding supermassive black holes whose accretion disks outshine their host galaxies. Under this explanation, the LRDs, little red dots, are primarily AGN, and their inclusion in galaxy counts artificially inflates the observed luminosity function. Remove the AGN contribution, and the remaining purely stellar galaxies might not exceed the theoretical predictions by such a large factor. The 2025 Nature paper confirming LRDs as young supermassive black holes in dense ionized gas halos lends support to this interpretation. If LRDs are AGN, their very high luminosities are powered by gravitational accretion, not by star formation, and accretion is far more energy efficient than nuclear fusion, meaning even modest mass black holes can outshine galaxies of much larger stellar mass. The AGN explanation is currently the most actively studied, and it has some power to reduce the apparent excess, but it introduces its own problem. If LRDs are AGN hosting overmassive black holes in the universe's first billion years, those black holes need explaining too. Trading a galaxy formation problem for a black hole formation problem is not a solution, it is a translation. The third category of explanation is the most radical, and the one most professionally resistant to rapid verification. Modifications to the lambda CDM model itself. Several theoretical groups have explored alternatives to cold dark matter, warm dark matter models, in which the dark matter particles have higher thermal velocities and form structures differently in the early universe. Fuzzy dark matter models, in which dark matter consists of ultralight axion-like particles with quantum properties that prevent structure formation below a certain scale. Interacting dark matter models, in which dark matter particles couple weakly to standard model particles in ways that alter the early matter power spectrum. Some of these models predict enhanced structure formation at early times, more massive halos assembling earlier, which would naturally produce more galaxies and more bright objects at high redshift. None of these modifications has been confirmed. None has achieved the status of a preferred alternative. But the fact that they are being taken seriously, modelled in detail, and published in major journals is itself a signal. A signal that the community, while cautious, is no longer certain that cold dark matter as currently parameterized is the full story. Now turn to the reionization tension. This is, in my judgment, the most precisely quantified of the JWST discrepancies and the one that is most difficult to explain away without invoking either new physics or systematic errors of a scale that would undermine confidence in the JWST calibrations more broadly. The tension between the JWST implied reionization timeline and the Planck CMB constraint is currently at the level of several sigma, not yet the 5 sigma threshold for a formal discovery claim in the particle physics convention, but more than enough to demand explanation. The two possibilities the Munoz et al. Paper identifies, enhanced recombination rates or new physics, are not equally tractable. Enhanced recombination, in which ionized gas reverts to neutral hydrogen more frequently than current models assume, would require detailed modelling of the structure of the intergalactic medium in ways that depend on the density distribution of gas on very small scales. That modelling is computationally demanding and uncertain. New physics is new physics. The population 3 detection in LAP-1b adds another dimension to the reionization story. If the first stars were, as the population 3 models predict, predominantly very massive, hundreds of solar masses, then their ultraviolet output per unit of stellar mass would be dramatically higher than the output of the less massive stars that dominate star formation in later epochs. This would mean that even a relatively small number of population 3 stars could ionize their local environment extremely efficiently, beginning the clearing process earlier than models assuming a more normal initial mass function would predict. Population 3 stars are, in effect, a missing ionizing term in the reionization accounting, and the potential detection of LAP-1b as a population 3 system suggests that this term may be larger than previously assumed. But LAP-1b's detection is not yet confirmed. It is a strong candidate, consistent with theoretical predictions, consistent with the spectroscopic data. It is not a detection with the certainty of MOMZ-14's spectroscopic redshift, which is anchored by a sharp Lyman alpha break and 5 rest UV emission line detections. LAP-1b is where the science sits at the productive boundary between strong candidate and confirmed detection, and that boundary, in modern observational cosmology, is inhabited by many of the most important findings. The confirmation, when and if it comes with deeper spectroscopy, will be significant. The Hubble tension sits in a slightly different position from the early galaxy problems because it is not primarily driven by JWST observations, but by the long-standing disagreement between local distance measurements and the CMB-based expansion history. JWST has contributed to the Hubble tension story primarily by providing new independent measurements of Cepheid variables in nearby galaxies at higher resolution than Hubble could achieve, and those measurements have, in several cases, slightly adjusted but not resolved the discrepancy. The most recent JWST Cepheid measurements, published in 2024 and 2025, continue to point toward an expansion rate closer to 72 to 73 km per second per megaparsec, in persistent conflict with the 67.4 value from the CMB. The resolution, when it comes, will likely require either identifying a systematic error in the Cepheid distance ladder that has somehow survived decades of scrutiny, or accepting that the lambda CDM model predicts an expansion history that does not match the universe we actually inhabit. There is one claim that circulates widely in popular science coverage of this topic and deserves explicit correction here. The suggestion that JWST's early galaxy discoveries imply the universe might be older than 8 billion years, perhaps twice as old, perhaps older still. This claim, originating from a paper by Canadian astronomer Rajendra Gupta in 2023, received disproportionate media attention, but has not found acceptance in the professional astronomical community. The paper invoked a tired light model, the hypothesis that light loses energy as it travels through space, producing the observed redshift without the universe actually expanding, in combination with a varying physical constant model. Tired light models have been definitively ruled out by multiple independent tests over several decades, including observations of type-ia supernovae brightness duration relationships that are only explicable in an expanding universe and observations of the cosmic microwave background spectrum that precisely match the Planck blackbody prediction of an expanding, cooling cosmos. The universe's age of approximately 13.8 billion years is not in dispute. What is in dispute is a narrower but still fundamental question. How fast did the first structures form within those 13.8 billion years? This distinction matters enormously. The age of the universe claim is a red herring, dramatic, shareable, and wrong. The actual finding that the first billion years of cosmic history produced structures in quantities and at masses that the standard model did not predict is more subtle, more precisely constrained, and ultimately more scientifically significant, because it is a specific quantifiable discrepancy that will eventually be resolved by specific quantifiable physics. The ISSI Breakthrough Workshop paper in Nature Astronomy, authored by more than 50 leading researchers, attempted a consensus accounting of where things stood as of 2025. Its language was careful, its conclusions measured, and its overall tone was one of collective intellectual excitement rather than crisis. The findings, as summarized by the paper's co-chairs, represent the rewriting of our understanding of cosmic origins. Not the demolition of existing understanding, but the active revision and extension of it. Galaxies and black holes formed earlier than expected. Chemical enrichment proceeded faster than expected. The sources of reionization are more numerous and more efficient than expected. Individual ionized bubbles, carved by early galaxies, have now been directly mapped. The picture is becoming more detailed, more constrained, and, in the specific sense that a map becomes more useful when it shows terrain that was previously blank, more accurate. But, and this is the tension that makes the field so alive right now, more detailed and more accurate does not mean more consistent with the theoretical framework that preceded the observations. JWST has been consistently finding that the early universe looks nothing like the simulations that were regarded as state-of-the-art as recently as 2021. Those simulations were not bad science. They were the best available predictions based on the best available understanding. The fact that they are wrong is not an indictment of the scientists who made them. It is an indictment of the limits of our prior knowledge, and a vindication of the argument that the only way to test a model of the early universe is to actually observe the early universe directly with an instrument capable of the task. For 30 years, we made predictions about what JWST would find. JWST launched and found something different. That is not a failure. That is science at its most productive. A hypothesis meeting the universe, and the universe refusing to confirm the hypothesis. The next step, building the new hypothesis, testing it, refining it, is already underway, and the data from which it will be built are still coming, because JWST is still operating, still pointing, still collecting photons from the edge of everything. The record is already broken again. By the time you watch this, it may be broken a third time. The history of JWST's record-holding detections has been a sequence of brief triumphant moments, each new most distant galaxy ever confirmed, supplanted within months by the next one, and there is every reason to expect this sequence to continue as the telescope's deep survey programs accumulate more data and the spectroscopic follow-up of photometric candidates proceeds. But the significance of what comes next is not primarily about the record. The record, the redshift number, the look-back time in billions of years, is the headline. The science is in the details beneath it. Every new confirmed high redshift galaxy adds a data point to the luminosity function, adding statistical weight to the question of whether the early universe's galaxy population truly exceeds standard model predictions, and by how much. Every new spectrum carries chemical information, the presence or absence of heavy elements, the emission lines that trace the ionization state of the gas, the nitrogen or carbon abundances that speak to the nature of the underlying stellar population. Every ionized bubble detected around an early galaxy adds a constraint on the timeline of reionization. The record-breaking is the attention grabber. The data are the substance. What specifically is coming in the near and medium term? Several observation programs either underway or approved will push the frontier further. The JWST's deepest ever spectroscopic programs, including extensions to the JWST survey and new proposals from teams at MIT, Geneva and Cambridge, are targeting photometric candidates at Z15, redshifts corresponding to look-back times greater than 13.6 billion years, to epochs when the universe was less than 200 million years old. The theoretical models, even the revised ones, predict that at those redshifts, galaxies should be truly rare and dim. If JWST finds bright, massive galaxies there, as the trend of the last 3 years suggests it might, the discrepancy with lambda CDM will be more severe, not less. Meanwhile, the Nancy Grace Roman Space Telescope, whose launch was approved and preparation ongoing as of 2025, represents the next major leap in survey capability. Roman's primary mirror is 2.4 meters in diameter, similar to Hubble's, but its field of view is 200 times larger than Hubble's and more than 100 times larger than JWST's NIRCam. Where JWST can survey a postage stamp of sky to extraordinary depth, Roman can survey a swathe of sky to significant depth, finding the rare, bright, high redshift galaxies that JWST is too narrow field to discover efficiently. Team members on the MOM-Z14 discovery paper were explicit. Roman will boost the sample of bright, compact, early galaxies from the dozens currently confirmed by JWST into the thousands. The statistical argument, currently compelling but still limited by small numbers, will become overwhelming or will disappear. Either outcome would be transformative. The Atacama Large Millimeter Sub-But Millimeter Array, ALMA, the radio telescope system in the Chilean Atacama Desert, is already being used to follow up JWST's early galaxy and LRD discoveries. ALMA observes at millimeter and sub-millimeter wavelengths, sensitive to cold gas and dust in ways JWST is not. The combination of JWST's infrared imaging and spectroscopy with ALMA's radio measurements creates a multi-wavelength portrait of early galaxies unprecedented in its completeness. The team that confirmed the LRD CAN-UC's LRDZ8-6 has already announced plans for further ALMA observations aimed at characterizing the cold gas and dust content of the galaxy and refining the properties of its central black hole. Those observations will come, and they will carry, in the ratio of molecular gas to stellar mass, in the dust temperature, in the kinematics of the gas around the central black hole, direct information about the physical conditions that allowed an overmassive black hole to exist in a galaxy less than 600 million years old. The population 3 detection in LAP-1b, if confirmed, opens an entirely new branch of JWST science, the systematic survey for population 3 stellar systems across a range of redshifts using gravitational lensing to amplify signals that would otherwise be below the detection threshold. Gravitational lensing, the bending of light by the gravity of foreground galaxy clusters, which magnifies and distorts the images of background objects, has already been used extensively in JWST deep fields to reach objects that would otherwise be invisible. The same clusters that serve as cosmic magnifying glasses for distant galaxies can be used to search for POP3 systems, and the survey strategies to do this are already being planned. The Hubble tension, meanwhile, is approaching the point where it will either be resolved or formally acknowledged as a signal of new physics. Several independent groups are pursuing JWST measurements of Type Ia supernovae in nearby galaxies, using the telescope's infrared capabilities to minimize the dust corrections that have been a source of systematic uncertainty in the distance ladder. These measurements, when accumulated in sufficient numbers, and the accumulation is already well underway in 2025 and 2026, will either tighten the local Hubble constant measurement and deepen the tension with the CMB value, or reveal a systematic error that has been hiding in the Cepheid calibrations for decades. Either result will be significant. A deepened tension means new physics, almost certainly. A resolved tension means the measurement systematics were more subtle than previously recognized, and that conclusion would itself reshape how the field approaches precision cosmology. And then there is the question of the LRDs, 341 confirmed as of 2025. The Nature paper proposing they are young supermassive black holes in dense gas halos is compelling, but it is not the consensus. Alternative explanations are still being modelled and tested. The Penn State proposal of black hole star atmospheres, objects at the theoretical boundary between stellar and compact, represents one of the most exotic possibilities currently in the literature, and while it strains credulity in the way that all genuinely exotic scientific proposals initially do, it has not been definitively ruled out. The definitive characterization of LRDs will require, at minimum, deeper spectroscopy at higher resolution than currently available, combined with multi-wavelength observations from ALMA and future X-ray telescopes, capable of detecting the faint hard X-ray emission expected from AGN that is currently invisible from LRDs, their unusual weakness in X-ray being one of their most mysterious properties, given that AGN are typically bright X-ray emitters. The Athena X-ray Telescope, ESA's next major X-ray observatory planned for launch in the early 2030s, will be essential for this. JWST can see the LRDs. It can spectrally characterize their optical and near-infrared emission, but it cannot see their X-ray emission, and the absence of X-ray emission from objects that, if they are AGN, should be X-ray bright is one of the deepest puzzles in the current LRD mystery. The 2025 Nature paper proposed that dense neutral gas surrounding the black hole absorbs the X-rays before they can escape, a so-called Compton-thick obscuration scenario. Athena will be able to test this directly, searching for the hard X-ray photons that would penetrate even a Compton-thick absorber. If Athena detects those photons from LRDs, the AGN interpretation will be confirmed. If it doesn't, the mystery deepens further. What the next decade of observations will not deliver, and what I want to be precise about, because this is a conversation about science rather than prophecy, is a final, definitive, comfortable resolution of all the questions JWST has opened. That is not how the scientific process works. Each answer generates new questions. Each confirmed detection defines new uncertainties. The galaxy that holds the distance record today will be surpassed. The model that best fits the data today will be refined. The tensions that are currently at several sigma will either cross the 5 sigma threshold and become confirmed discoveries of new physics, or will resolve as systematic errors and return us to a modified but recognizable version of lambda CDM. In either case, in every possible resolution, the universe that JWST reveals will be more complex, more detailed, and more accurately described than the one we entered with in 2021. That is the only guarantee that careful, systematic observation has ever provided, and it is, if you stop and hold it for a moment, a guarantee that reframes the human relationship to the cosmos. We are not converging on a final picture. We are walking toward a horizon that recedes as we approach. But we are walking, we are measuring, and every step we take, we carry with us the light from the universe's very first moments. Light that, 13.5 billion years after it left the galaxy we call MOMZ-14, has found at last something capable of receiving it. There is a particular quality of patience in starlight. The photons that JWST collected from MOMZ-14 on May 16, 2025, left their source 13.5 billion years ago. They did not know, could not know, being photons, that there was no one to receive them. They crossed the expanding universe in the only way light knows how, in a straight line at the only speed available to them, through a cosmos that was growing around them as they travelled, stretching their wavelengths, cooling their energy, reddening them from the ultraviolet of a hot young stellar nursery to the infrared registered by JWST's detectors. For 13.5 billion years, those photons existed in a universe in which there was no eye capable of seeing them. Stars formed and died, galaxies assembled. On an unremarkable spiral arm of an unremarkable galaxy, a species of primate built cities, wrote languages, invented mathematics, and eventually aimed one of those mathematical traditions at the sky. And on the 16th of May 2025, those 13.5 billion-year-old photons arrived at a mirror made of beryllium and gold, floating in the cold one. 5 million kilometers from that species' home world, the light had waited 13.5 billion years for someone to be ready. We were barely ready. We are still, in many ways, not ready for what it told us. What strikes me most, in sitting with the JWST findings over these months, is not the specific records, not the redshift of 14.44, not the 45,000 galaxies in a postage stamp of sky, not the supermassive black hole at 570 million years, remarkable as all of those are. What strikes me is the systematic nature of the surprise. JWST was not built to find anomalies. It was built to confirm and extend an existing framework, to add detail and precision to a picture that was considered, in its broad outlines, correct. The scientists who designed its observation programs knew what they expected to find. They had made predictions, they had run simulations, they had spent decades preparing the theoretical scaffolding that JWST would test, and the universe disagreed. Quietly, systematically, across every high redshift observation program, across the luminosity functions and the reionization timing and the black hole mass fractions, the universe came back with data that said, not quite, not as expected. Something was happening in the first billion years that we did not fully account for. We do not yet know exactly what that something was. I find this genuinely moving. Not in the way that spectacle is moving, not in the way that a beautiful image of a deep field full of 10,000 ancient galaxies is moving, though that too carries its own weight. I find it moving in the way that honest intellectual confrontation is always moving. Here is a species, occupying a thin blue skin of biosphere on a rocky planet, orbiting an ordinary star in the outer arm of a spiral galaxy in the unremarkable Virgo supercluster, that has managed to build a machine capable of seeing to the edge of the observable universe, capable of detecting the light of the first galaxies, the chemistry of the first stellar populations, the ionizing bubbles carved by the universe's first sources of light. And the first thing that machine has told us, clearly and repeatedly, is that we had more to learn than we knew. That is the condition of genuine inquiry, not the reassurance of confirmed hypotheses, but the productive disorientation of confronting something you did not predict. Science does not always give you what you expect. It gives you what is there. And what is there, at the edge of the observable universe, is a universe that was more active, more energetic, more chemically complex, more structured, more full of light and mass and organised matter in its very first moments than anyone had imagined it to be. The question of what this means for us, for where we come from, for what kind of universe we find ourselves in, for the likelihood that the processes which eventually produced beings capable of asking these questions were commonplace or rare, that question remains open. It will remain open for a long time. The data JWST is generating will take decades to fully analyse, model, and understand. The theoretical revisions it is forcing will require the work of the next generation of cosmologists, people who are currently in graduate school or completing their undergraduate degrees, or perhaps not yet born. This is the nature of science at the frontier. You do not arrive at an answer and stop. You arrive at a better question and continue. MOM Z14 is not the end of the distance record. It is a moment in a sequence that began with Hubble's first deep fields and will continue with instruments we cannot yet name, built on technologies we cannot yet imagine, for as long as our civilization maintains its astonishing precarious habit of looking up and asking what is there. The universe began 13.8 billion years ago. We have been looking at it seriously, with instruments capable of genuine discovery, for perhaps 400 years. We are extraordinarily early in this project. The edge of the observable universe sits at a distance of 46 billion light-years in every direction, and we have begun, only begun, to read the documents that its oldest light delivers to us. Every one of those documents is written in a language we are still, together, learning to translate. What JWST found at the edge of the universe is not a conclusion. It is a door, and behind the door is not an ending, but the next room in a structure so large that standing inside it, you cannot see the walls. We are the generation that built the instrument, the generation that found the record-breaking galaxy, the generation that discovered the tension in the model and began the work of understanding why it exists. We will not be the last generation to build a telescope or to find something unexpected, or to sit with a piece of data and feel the particular quiet, irreplaceable experience of not knowing, of being genuinely uncertain in the face of genuinely new information. That feeling is not confusion. That feeling is not failure. That feeling is exactly what knowledge looks like at the moment of its growth. It is uncomfortable. It is necessary. It is, in its own way, the most human thing there is. The light from MOMSI 14 travelled 13.5 billion years to reach us. It found us looking. Keep looking.